Komal, all other people are coming or nobody is coming?
Oh, yes, sir. They are coming. They are coming.
Okay, okay, thank you. We'll wait for 1 to 2 minutes.
Okay, okay, sir.
So I think we should start now, I guess. So can you see my screen now?
Yes, sir.
Okay, good. So okay, so I think today I am going to describe few algorithms for computing power of a number in the ring integer modulo n, especially in other words modulo m, and this is quite useful in many applications of computational number theory. So let me define few things before we can start. Some notations. We will define log n as 1 if n is equal to 0, and 1 plus log of 2 base mod n if n is not equal to 0. Okay, so this log n counts the number of bits in the binary representation of the integer. So this log n counts the number of bits in the binary representation of the integer n. Okay, also there is another function normally defined is known as mu function. It's a two variable function which is m times log n times log n if m is greater than or equal to n, and it is n log m log m otherwise. So when m is less than n, then we have this thing. So now the cost of basic arithmetic operations. So very basic operations that we know. So if the operation is a plus b, so naive bit complexity is log of a plus log of b, and best known is big O of log of a plus log of b. Okay. Similarly, subtraction a minus b is log of a plus log of b, and best known is also the same thing. Multiplication is log of a times log of b, and the best known is big O of mu of log of a comma log of b. So mu of the function, I have used mu mn function which is described above, and the division is a is equal to some quotient plus remainder. So naive bit complexity is log of q times log of b, and best is mu of log of q comma log of b. So these are just summary known information to you. Now actually one more important result. Last time we discussed about Euler-Totient function phi of n, if you remember, all those numbers less than n and which are co-prime to n, right? So if we if phi n is defined like that, so for example, you know that we have shown that if p is a prime, then phi of p is p minus 1, if you recall from the previous class. So then there is a very fundamental result which says that a raised to power phi n is congruent to 1 mod n. Okay, so this is a very important result related to finite fields as well, the specific case. Okay, another theorem that I want to say about the modular arithmetic, we can add and subtract elements of Zn integer modulo n in big O of log n bit operations. Okay, and we can multiply using big O of log of n whole square bit operations. Okay, and in fact the proof depends on this fact. I am not proving it, but I think you can look at it. Note that if 0 is less than or equal to a, b is less than n, then a plus b mod n is nothing but a plus b if a plus b is less than n, and a plus b minus n if a plus b is greater than or equal to n. So you can see that actually no division is required if you do it something like this, So no division is necessary. Fine. So I think now the important thing that we wanted to discuss today is modular expo n modular exponentiation. So what we want to do now, given a natural number m, and suppose a and e are integers, then our task is to compute a raised to power e mod m. Now you know that if I have to compute this, so I have to multiply a e many times, a into a into a into a e times, and then divide it by m and see what is the possible remainder, right? So this is a bit normal thing. In fact, without loss of generality, we assume that e is positive. Suppose e is negative, what will happen then? Okay, suppose e is negative, its value is e is minus t, where of course t is positive, then only it is negative. Okay, then a raised to power e is same thing as a raised to power minus d, which is same thing as, because d is equal to e is equal to minus d, is same thing as a inverse of d mod m. So that means if I have to find a raised to power minus d, what I can do, I can compute the inverse of a and raise it to power d. So essentially it is enough for us to assume that we want to compute this exponentiation when e is positive, right? Anything negative can be converted like this to positive thing. Okay, so I want to compute this a raised to power e mod m, where e is positive. So now this method that I am going to describe is actually mentioned in Indian literature by Pingla. Pingla, the person who gave all these things for for Sanskrit grammar, you know. So actually, Sanskrit grammar was given by Panini. Pingla was also there at the same time. So he has given this, you know, this trick actually, how to compute uh, power fast. So what you do here, so let E, the exponent, which is a positive thing we have assumed, is something like ES minus 1, ES minus 2, dot 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 E1, E0, base 2. So EI is either 0 or 1. Okay. Okay. Now, so this is our actual exponent. So if I put this exponent, so basically what we are doing, if we have to compute a raised power E here, I am just writing E as a binary exponent, you know. So write down the binary representation of E and see, can we use this technique depending upon the bit of E is either 0 or 1, we can do the calculations, you know, certain calculations. So the raise to the power can be simplified. In fact, we will need another thing, what is known as partial exponent. So partial exponent we define as xi. It is starting from es minus 1, es minus 2 up to ei. You note that this I means up to component I here in binary 2. And this is defined for all I from s, s minus 1, 1 and 0. Okay, this is now defined as partial exponent. Also, xs should be interpreted as 0. Okay, that is there. Now let bi, I am defining another expression, bi is congruent to a raised to power xi. This partial exponent if I raise mod m, then what will happen? I am going to show you now how this you know, squaring and multiplying is an easy way to describe all the operations. So let bi is a raised for xi mod m. So basically we wanted to compute a raised for e. Okay, so e is the full exponent. I have written the binary expansion. Now I am writing partial exponent xi to be like this, and then we look at a raised for xi and call it bi. Initially, okay, bs is congruent to 1. Okay, so now keep on counting. Keep on, sorry, not counting, 1 minute. What we do now, keep on computing bs minus 1. Bs is starting point, initialization. Bs minus 1, then bs minus 2, until we get b0, last one, which gives us the actual value. Okay, so since now again it's interesting observation, xi is nothing but 2 times xi plus 1 plus ei. See, if you look at the xi and xi plus 1, the relation is, because it is in base 2, so that's why this power is 2 here, this 2 is multiplied here, you know. So what I'm saying that xi can be written as 2 times xi plus 1 plus ei. This relationship is there, and hence using this relationship I can compute bi, which is a raised to power xi, same thing as a raised to power xi plus 1 times 2 into a raised to power ei. By substituting this expression, we get this. This is nothing but bi plus 1 square into a raised power ei mod m. Okay, so that means what we are doing essentially at every step, because of this partial exponent, we square and then multiply, square and multiply, square and multiply. Okay, so this is the technique. So that's why this technique is known as square and multiply method. Okay, so this suggests us that I can write down a nice algorithm which will just use square and multiplication. So let me show you how it works. So our algo is initialize t is equal to 1 mod m. Okay, I'm just writing a loop for I is equal to s minus 1, I will equal to 0, subtract I. Then we have set t is equal to t square. We are computing square modulo m, right? So now, depending upon the value of ei, the ith component of the exponent, if it is, that component will be either 1 or 0, right? If it is 0, we ignore, but if ei equals 1, set we multiply, t is equal to ta mod m. Okay, and then finally we return t. Okay, so here in this step we are doing the square, and here we are multiplying if ei is equal to 1. If ei is equal to 0, we are ignoring that actually. So let me show you a brief example. Now, since the size of s is big O of log e, this loop is executed in at most big O of log e. Okay, so that is the complexity. So let us see an example here. Okay, so what we need to do, suppose we want to compute 7 raised to power 13 mod 31. So m is equal to 31, a is equal to 7 here, right? And e exponent is 13. I can write down the binary expansion 1101. That's a binary expansion of it. Okay, so how we can use this algorithm, square and multiply algorithm? So we have I exponent di xi is equal to e3 pi 2. So t after square and t after multiplication and bi, the value of bi actually. So we need to look at the value of bi all the time. So when I is 4, ei is not used here. This is 0. All these are blank. bi is 1. When I is 3, so now the first is 1 ei component, so I'll use 1 here. So 1 at base 2 is 1. So here we have 1 square. Remember the algorithm was t square, right? We are squaring, and then reducing it to modulo 31 is 1. Everything is mod 31. Okay, mod 31, mod 31. Okay, is 1. So 1 into 7. Now you multiply. So this is 7. So bi is 7. Next, I is equal to 2. Next bit is 1 of ei. So this is 1, 1, 2, which is 3. 7 is square. is 18 mod 31. 18 into 7 is 2. So B2 is 2 here now. Okay. Next we go to 1. Now ith component EI is 0. So now you remember this is 6. So 2 square. Okay. So EI is 2 square. T square. We are computing a square. 2 square is 4 mod 31. Now here this multiplication is skipped, right? Multiplication is skipped. Why? Because EI is 0. If you remember. So we have to multiply only if we have to multiply here only if EI is 1. Okay. Otherwise we skip. So the multiplication is skipped and the value turns out to be 4. Next we go to I is equal to 0 loop. EI is 1 now. So this is 1 1 0 1 2 is 13. So 4 square is 16 and 6 modulo 31 and 16 into 7 is 19. So BI is finally 19. Therefore, 7 raised to power 13 is equal to 19 modulo 31. So I hope you might have looked at this algorithm, of modular exponentiation. Now, actually, a little bit of modification was done in this algorithm in 1986 by Barrett. So, we can improve the algorithm a bit by using a reduction in the division, because the division is the only costly operation. The cost of division can be improved. So I think I can talk about it briefly here. So this was given by Barrett in 1986 actually. So let me explain this with some assumptions here. Let base be, so basically let B be the base. Okay, so I can assume that so B is something either of the form 2 raised to power 32 or 2 raised to power 64. Okay, and this algorithm works for any B greater than 3. So first thing, so because you see we need to compute A raised to power E mod M, right? And what we are doing is square and multiply, right? So what we can do now, write down M as the modulus M can be written as ML minus 1, ML minus 2, M1, M0 in base B. Okay, actually now, so M is represented in base B number. We pre-compute actually something. We pre-compute capital T. T is a value. B raised to power 2L divided by M, and the greatest integer. So given a 2L digit number, integer, 2L digit integer I should say, multiplying x is equal to x2l minus 1, x2l minus 2, x1, x0 in base B of two elements of Zm and integer modulo m, because we are working with integer modulo m, and pre-computed t, we can improve the algorithm t. Okay, so how do we do this? Let me show you. Okay, so what we do here, first I should mention the algorithm, and then I will show you how it works. So what we do, actually, you see, we need to improve on the division, right? So I will, so normally, in the division, there is a quotient and there is a remainder. Okay. So we will compute approximate quotient and approximate remainder. And from that, we'll compute the actual quotient and actual remainder. So the algorithm says that you compute capital Q, which is potential x divided by b raised to power l minus 1. You also compute q is equal to qt, and q is equal to divided by b raised to power l plus 1. Okay, then you compute r as x minus q into m modulo. I will explain this in a minute actually. Modulo b raised to power l plus 1. So while r is greater than or equal to m, set r is equal to r minus m, and finally return r. So this actually will give you the remainder. So we want to compute the remainder. 1 minute.
Excuse
Return.
me, sir.
Yes.
सर यहाँ पे सेट का मतलब क्या है? While r is greater than equal to m set.
हाँ, so basically हम subtract कर रहे हैं. एक्चुअली क्या है कि जो हमारे पास अप्रोक्सीमेट रिमाइंडर आएगा ना, उसको m से कितना दूर है वो जानने के लिए m सब्ट्रैक्ट करते जाएंगे एज ऑफन एज नीडेड एक्चुअली. ठीक है.
Okay.
Okay, so let me give you actual explanation how it works, and then I will show you an example, and that will be enough. So what we can do actually here, we know that one can write x is equal to qm plus r. Right, this is the normal formula. Quotient, q is quotient, r is remainder, right? Where 0 is less than or equal to m minus 1. And we know that actual quotient is x divided by m, right? This is the greatest integer thing. So what we compute now here in the algorithm, actually, what we are computing is the following. Compute approximate quotient, capital Q. मेरी राइटिंग बहुत खराब हो गई है एक्चुअली, इस पे लिखते लिखते. ओके, compute approximately. So how we do this? Capital Q is nothing but approximate quotient is greatest integer of x divided by b raised to power l minus 1 times b raised to power 2l divided by m divided by b raised to power l plus 1. We compute this. Okay, and I think after some calculations, I just write a claim. Probably you can try to verify it, that Q lies between small q, and so it is little, so in the neighborhood of q actually, capital Q. The approximate quotient lies between q minus 2 and q. Okay. Then we compute approximate remainder, capital R. Okay. So we know that, so actual remainder we know, actual remainder is what? R is actually x minus qm, right? एक बार हमको q पता लग गया क्वोशंट, तो हम रिमाइंडर ऐसे निकाल सकते हैं. तो हमारे पास अभी क्या है कि अप्रोक्सीमेट क्वोशंट है, तो आवर कैपिटल रिमाइंडर विल बी x माइनस कैपिटल q टाइम्स m. x की तो जो वैल्यू दी हुई है कैपिटल q इज अप्रोक्सीमेट क्वोशंट. ओके. Now we know that q minus 2 is less than or equal to capital Q is less than or equal to q. Using this inequality, you can show that approximate remainder cannot exceed 3m. Okay. And further, actually, since m is less than b raised power l, I think earlier assumptions, and our b is, I mean, in fact, this is a kind of, we are putting a condition that if b is greater than 3, remember we mentioned that the base, this algorithm works if base is greater than 3, then r is less than b raised to power l plus 1. So actual r is computed now, okay, by subtracting from capital R by subtracting m as often as is necessary. Okay, so let me show you an example, and I think that will show you the case. So what we are doing, again I'm repeating, we are computing approximate quotient, okay, then approximate remainder, and from that approximate remainder, actual remainder R is computed. So this is the important line actually. Actual R is computed from R by subtracting m as often as is necessary to compute the actual division. Okay, so let me show you an example here. It's a bit, actually I would invite you to verify the details of this example on PeriGP software, because if you want to do it by hand it will be too lengthy. So assume that our base is 2 raised to power 8, just as an example 256, which is easy to understand. Okay, and our m is 1 2 3 4 5 6 7 8. You can see that it is nothing but 188, 97, 78 at base B. Okay. Okay. Next, so this implies that we know that L is equal to 3 here, which is fine. L is equal to 3. Now, if I want to compute, so suppose A is given, A is 1058539 So in base B, this value is 161, 133, 47 in base B. All these things you can compute it using the PeriGP. You don't have to do it by hand. And suppose B is equal to 851, 2056. In base B, this is 129, 226, and 56 in base B. So A and B are, suppose A and B are multiplied. So we get X is equal to A into B as 901034409738996. Of course, by doing hand will take a lot of time, but with the Peri GP you can compute these things easily. 81, 242, 215, 151, 160, 72. Base B. Base B is 256. Now we do the pre-computed quantity. Capital T is B raised to power 6 divided by M. This is nothing but 22799,474 in decimal, and in base B this is nothing but 191,228,114 base B. So capital T is actually in general L plus 1 digit number actually. Okay, so now using capital T, which is a pre-computed quantity, using capital T, small m, and x as input for the algorithm. Input for Harris algorithm. So what we do, we compute x divided by b square because L is 3 here, right? So this is 31346299112696126. So again, I'm saying that you need to verify these things using PeriGP. This is 81, 242, 215, 151 at base 2. We discard two least significant digits of x here because we need to take the greatest integer. So multiplication of this with capital T with capital T gives 31346299115896126, which is in base 2 is 111, 93, 74, 255, 211, 125, 62 in base B. So finally we divide this by b raised to power 4. Okay. Again, discard last 4 significant digits. So we basically discard 4 least significant bits. Okay. So to obtain approximate Q as 7298378, which is in base B 111, 93, 74 base B. So Q is actually 1 smaller than the actual Q. Okay. So the approximate R is computed as x is equal to 90103 440973896. Okay, and then we have qm is equal to 9010342471028. So capital R is nothing but x minus qm, which is 162,63612. I'm not writing base B here, you can write it down. So the correct value of R is x reminder m, basically capital R minus small m is equal to 3917934, which is in base B is 59, 200, 110. Of course, this is bit lengthy, right? This is 4, this is 0, this is 9, this is 4, 3. Okay, so this is how I think you compute, so capital R is larger than M, so we actually subtract here. Finally, we got this answer as this is also 4 here. So this algorithm is a little bit, I mean, of course, it is a little bit better, but I think, that's okay. So finally, this is for the exponentiation. So there we mentioned about two things. One is the actual algorithm, square and multiply, and the improvement. Now, one last result I want to mention today is linear congruences. So we need to solve equations like AX congruent to B mod M. I think this you might have read earlier, where M is natural number and A and B are integers. I think, yes. So there is a result. How do we solve it? The theorem is given. It's a very nice theorem. So I'm not proving this because this you may be knowing it from your earlier discrete math course. GCD of A and M. Okay. So we can solve the equation if and only if D divides B. अगर इन दोनों का GCD B को divide करता है तो we can solve it. So there are two cases. If D divides B, then all solutions are congruent to each other. And this congruence is modulo M by D. Second, if GCD of A and M is 1, then equation has unique solution. Unique solution. Okay. So this is the final result. So I think that's all for today. I guess, okay. So you got, so we talked about exponentiation and so on. Now I am going to cover some background about Chinese remainder theorem, and then we'll talk about quadratic residues, because those things are important for the later on calculations, when we want to describe other algorithms in number theory. Okay. So I think any question up to this point?
नो सर, नो सर।
ओके, सो हम लोग को एग्जाम लेना है या वो पेपर अभी तुम लोगों ने किया है कि नहीं? फिर वो
सर चालू
असाइनमेंट
कर दिया भाई, सर पेपर चालू कर दिया।
चालू कर दिया, ठीक है, गुड गुड।
हाँ सर,
तो आई
फाइनली
थिंक
सर।
कुछ अगर वो पेपर आई थिंक देर आर डिफरेंट वेज यू कैन सबमिट द थिंग, यू मे बी यू कैन मेक ए नाइस पीपीटी इफ यू वांट, प्रेजेंटेशन। दो लोग को मिलके करना है ना,
हाँ
एक
सर।
पीपीटी में बता सकते हो कि व्हाट वर्क हैज बीन डन, समराइजिंग। ओके, दैट इज द इजी थिंग एक्चुअली, बिकॉज यू हैव टू प्रेजेंट योर थॉट्स नाइसली। ओके, तो चाहो तो एक पीपीटी बना सकते हो अच्छी सी, ठीक है?
राइट सर।
So fine, I think in the next class we will meet. We will be doing a couple of more backgrounds, and then we can move on to some more finite field stuff. Especially in terms of complexity. Okay. Thank you.
थैंक यू सर, थैंक यू सर।
हाँ,
सर आपका कॉलेज खुल गया है क्या, मतलब अभी लॉकडाउन के बाद?
अभी नहीं खुला है, अभी नहीं खुला है। क्या तुम लोग को इधर आना है क्या? तब तो बहुत ही अच्छा होगा।
अच्छा, मतलब वही है, मतलब कोरोना का अभी भी डर है सर, कि मैं मुंबई में काफी बढ़ गया अभी वापस से।
अच्छा, यू आर इन मुंबई राइट नाउ ना?
यस, आई एम इन मुंबई।
ओके ओके। या अभी तो थोड़ा बढ़ गया है, बस पिछले हफ्ते से थोड़ा बढ़ रहा है, राइट? देयर
राइट
इज
राइट
एन
सर,
इशू।
आसपास रेस्टोरेंट बंद हो रहा है मेरे वापस से अभी।
अच्छा अच्छा,
हाँ सर।
ठीक। हाँ, अभी तो खुला नहीं है एक्चुअली, अभी तो नहीं खुलेगा। मेरे को नहीं लगता है कि जुलाई तक कुछ खुलेगा यहाँ पे।
ओके ओके सर।
तो हम लोग कभी मिलेंगे नहीं ऐसे ही वर्बली होगा बातें, आई गेस, राइट?
ओके
और
राइट
अनलेस
सर।
यू कम सम टाइम, और आई कम टू IIT Jammu because last time I went to Jammu to 2018, I guess.
हम्म।
So so I am working with I think your Gaurav Washne sir है ना, Gaurav Washne।
हाँ हाँ जी सर।
गौरव जी के साथ काम कर रहा हूँ मैं, और सरताज इज ऑल्सो नोन टू मी, एंड योर डायरेक्टर एनीवे।
ओके ओके।
Anyway, so hopefully we will meet sometime. I don't know. So if you can do something, so I was thinking, if you make some progress and we can do some new things, that will be really nice. Anyway, so I think I have also sent one one course on quantum computing. I think you might have seen this. So if you don't know quantum computing, maybe you can do this five-day course, which is only 2 hours per day, kind of 3 hours per day actually, for 5 days, and you can learn the basics of quantum computing if you want to learn actually. Okay.
ओके सर।
Okay. ठीक है फिर, we'll see you in the next class. Thank you.
थैंक यू सर।